So I was asked if it's possible to reveal the bits from the cipher sums that we get for full homomorphic encryption, say for this example here. So the method that we're using is to take our bit, take one bit at a time, we create a random number, we multiply it by 2, which will make it even. Then we take a random value q and we multiply it by p. So the core of this, to make sure that it works, is that p must be odd. So when we get a random number, we should have a 50-50 chance of the cipher bit, the cipher value, coming out as odd or even. Okay, and I'll show you that in a little minute. Okay, so there's our ciphering process. We come up with a p-value, that's our secret key. And I make sure that it's odd by multiplying it by 2 and adding 1 onto it. And then that goes into here. We generate Q and R, and then we generate our cipher value. Okay, so in this case we're using an adder circuit. We create our cipher bits and we put them into our adder circuit and then get the result out. Okay, so if we run it a few times, then hopefully we should see, so that's even, odd, even there. We'll try it again. Even, odd. Try it again. And we get odd, even, odd. Okay, so each time we're running it, we're getting different values for different odd and even numbers for our cipher bits. And what we really want is that we make sure that if we run this enough times, we shouldn't be able to imply any of the bits. So we should get a 50-50 chance of them being odd and even. Okay, so here's my little sample code here. What I'm going to do is I'm going to run this through 10,000 times. I'm going to work out the cipher value that we get for the sum between two values, two 4-bit values in this case. And then I'm just going to detect if they're odd or even. Okay, so I can just concentrate on one of the bits, or I could take all of the bits. So I'll just show you just now if we just take one bit. So I'm going to take the first sum value, that's the least significant bit, and then run it through 10,000 times and we'll see how we get on. Okay, so it's now calculating with different values of p each time for an input of an addition. Just let it run through. For an addition of 3 plus 6. Okay, so it's 98.21. So that's an almost even split between odd and even. Probably if we ran it again, we'd get more even than odd. We have a 50-50 chance of that happening. So if I count up all of the bits, let's see where we get to. Okay, so we're running through. So our cipher bits should give us an equal chance of being odd or even. They're pseudo-random, so it's not perfect. We would want to go for full randomization if we were running this live. But we can see here, there were 20,000 even and 19,900 odd of odd, and there's virtually an even split between the two. Okay, so that's That shows the randomness of the homomorphic encryption method.